Okay, so thanks for coming back, I guess. I don't know what you have to do other than study dynamics. So in this video, I want to discuss section 16.7, which is on analyzing accelerations of rigid objects. So up till now, we've been talking about velocities of rigid objects. So we picked points on objects and kind of followed their motions in an absolute manner. Or if we knew one thing, we use relative velocity analyses to figure out the velocity of another point. Or we introduce the idea of an instantaneous center of motion. That gives another way to find velocities of quantities. And after you figure out velocity, well, the next thing you want to know about is acceleration, and that's what we're going to do today. I will just go ahead and give you a heads up. These problems are bigger with many more minus signs, and you have to be really rock solid in your conventions. Okay, so I want to lay it out. When I started to make this video, I thought, oh, you know, I ought to, actually, it's not for the video, but for the group problem, I thought, I ought to work through that one rather than doing it off on the fly. And, you know, I got through half of it, no problem. And then going from one page to the next, I missed a minus sign in one term, and it was just buried in the middle of some cross products. And it took me, I don't know, it probably took me a good 15 minutes to figure out what I did wrong. So just be careful. It's not that it's hard, it's big. And there are lots of little minus signs. So, okay, with that warning, let's get started. Okay. I know it's a little annoying to have this side view, but actually for me, I think it's a little easier to do it this way. Okay, so today we're going to talk about relative motion analysis, and you should be able to resolve acceleration of a point on a body into components that are translational and rotational, and then determine the actual acceleration of any point on a body using what's called the relative acceleration analysis. We'll go through it all. It mimics what we did for relative velocities, but it's just more complicated. Okay, you have the usual outline. Okay, so hopefully you've done the reading, 16.7. So let's go through these. If two bodies contact one another without slipping, and the points in contact move along different paths, the tangential components of acceleration will be the same or different. The normal components of acceleration will be the same or different. Think about it for a second. Okay, if the two objects are moving without slipping, their tangential components of acceleration must be the same. So the first blank is they're the same. The normal components, on the other hand, don't have to be the same. In fact, if the paths of the points aren't the same, and they do have the same tangential accelerations, they must not have the same normal acceleration, because the total acceleration must be different for the two. All right. When considering a point, question 2, when considering a point on a rigid body in general plane motion, its total acceleration consists both of an absolute acceleration, a relative acceleration, and relative acceleration components. B, the total acceleration is just the absolute acceleration components. Or C, it's only the relative acceleration components and is normal to the path. Or D, none of the above. Well, if you've done the reading, you'll know the answer is A. If I want to find the acceleration of a point, given some other position's motion, then it would be the acceleration of the basis point plus the relative tangential and acceleration and normal components of acceleration, or relative acceleration it is. So it has all, both relative and absolute data mixed in. So the best answer is A. All right, here's a kind of typical situation. There's some mechanism for a window. I think we actually solved something a little similar to this. And there's a link from A to C, right? And it rotates about a fixed axis through C, right? And since A moves along a curved path, well, let's kind of look at that. What's happening there? Yeah, so if I'm going to go try to draw on here, you can kind of see when they say it goes through a curved path, hopefully you can kind of see. So A is, at this moment, A is up here. But if you lower this window down, A is going to end up kind of over here, and it doesn't just follow a straight line path, it actually kind of follows an arc. So that tells you that point A is going to have, in general, both tangential and normal or radial acceleration. So it'll have both centripetal and tangential accelerations. So it'll, because it undergoes sort of complicated motion. Right. And so that's the kind of typical problem that we'd want to do. Basically, kind of knowing, let's say you know the acceleration. I may have missed. I'm sorry, I'm not exactly sure in this picture. I take it back. I drew, the idea is right. I misinterpreted the diagram. So let's kind of fix that. What they're telling me in words is that point C is fixed. If point C is fixed, that actually means A follows this kind of path. It's an arc. It's still an arc. So A has a general acceleration. And for that to happen, then B has to slide upwards. Okay. So I apologize for that. But the point still stands that A follows a general motion. So you should expect a pretty complicated kind of acceleration for different points. And a general problem that we might want to know in this section is, let's say you knew how fast rod or link AC is rotating. No, it's no omega and alpha for that. You might want to learn what is the acceleration and velocity of point B, things like that. Okay, so these mechanisms and these systems can get pretty confusing, and if you try to do it all in one shot, it's a nightmare. So don't. Instead, go through piece step by step and have a plan from the outset. I think that's a really big part of this, is just having a good plan from the outset, because the arithmetic in these problems is going to be large. There's going to be a lot of little steps, so having a plan is going to be very important. In case you're thinking, picking up on a theme, good, I hope so. Be careful. Have a plan. Here's another kind of problem you might have. You have a piston that goes up and down, and there's a crankshaft, and so as this goes up and down, B is going to rotate around A. It's going to have some sort of it's certainly not going to be a linear motion. So it's going to be a mix of rotations and translations. It's going to just in general be a lot of general planar motion. It'll be complicated. All right. Okay. So this is the basic formula we had. I'm going to switch over, kind of go through this a little bit, and then you can see where things are coming from. Okay. So the idea here is that we had a formula for velocity of one point in terms of the velocity of another point. We called this the relative velocity analysis. And so we said the velocity of, say, point B would be the velocity of point A plus the relative velocity of the two. So if I had an object, here's point B and here's point A, and say A is going that way and B is going that way, then later on you find that the object has done something like this, let's say, and what this is saying is you can think of the motion of point B as the same as the motion of point A, but on top of that, it's got a rotation. And we know that the form of a rotation would be omega AB cross the relative vector R, and it's a position of B relative to A. And these are all vector equations. Remember, rotational vectors point along the third direction. So in a plane, in the XY plane, all of the angular vectors are pointing in the Z direction. Okay, so this was our formula for relative velocity. All right, to find relative acceleration, we simply take the derivative of this. But what I want to emphasize is that this part right here is rotational. Okay, or you might, in physics 1, we would have said circular motion, general circular motion. So if you take a time derivative of this whole thing, then what you're going to get is an acceleration of B equals an acceleration of A. That's just the translational component. And then you have the relative term. And the relative acceleration, and we write it as B relative to A, where the relative acceleration, B relative to A, is simply, well, it's the time derivative acting on omega cross R, B relative to A, like that. And so that's fine. Let me insert another page. Okay, so so I need to work out, going back here, I need to work out the derivative acting of this. We can guess the answer and then we can verify that it's right. So our guess is, well, this relative velocity part was just a pure rotation. And we already know from physics 1 or any of the other point particle analysis you did earlier this semester that when you have a particle going around in a circle, you expect both a tangential and a radial acceleration. So it shouldn't be a big surprise that we get that the time derivative on omega AB cross R of B relative to A equals, well, it's going to have the radial component, or the book calls it the normal component, that points towards the center of the circle, or which in this case would be point from B back to A. So that's actually going to be minus omega squared times R vector B relative to A. The minus sign here tells you that the acceleration, the centripetal acceleration points back to the center of the circle. This is the centripetal acceleration term. And then plus that we have, so in physics 1, we said we had alpha R. But when we write that with cross products, we shouldn't be surprised that becomes alpha vector cross R B A vector. And if you think about it, alpha vector is in the Z direction, this points from the center of the rotation out to the outer edge. So that's radially outwards. If you think about that, Z cross R gives you a theta hat component, which is tangent then to the circle that you get centered on point A. All right, so that is where we're going to end up. And kind of using the Braille method, feeling our way through it. Let's work it out in detail. In detail, I would just take these derivatives and I would get omega vector dot A, B cross R vector B cross A plus omega AB cross, and then you would have the derivative on the relative vector. But the derivative, okay, so let me write that down. But this piece, oh, sorry, but this vector here was just a rotation. And so a derivative, so that means this is nothing other than omega AB cross RB slash A. The relative vector was a rotation vector. And so then you need to take a derivative on that. Oh, sorry. Went too far. The derivative, sorry, RAB was a relative position vector. The derivative on it was just going to be omega cross RAB. There you go. One too many layers here. All right. So now the first factor is simply alpha vector cross RB slash A. And this piece becomes omega AB cross omega AB cross RBA. And you have to be careful with cross products about the order, so watch your parentheses. Now, this vector, I actually tried to give a derivation in the first, I think it was the first lecture I did with you guys, and it was pretty bad. So I'm just going to quote, I'm just going to say using vector identities then, and you'll just have to trust me. So this becomes, well, okay, how about this? In general, if I have three vectors, there's an identity which relates these, and what you can say is this becomes B vector times A dot C minus C vector times A dot B. Okay. Hopefully that's something they showed you in Calc 3 or linear algebra. It's called the vector, the triple product. Usually if you do a search for vector triple product, you'll get a list of dot product stuff and whatever. Anyways, this will pop up too. All right, so this is true for any vectors A, B, and C. In particular, when I apply this to omega cross omega cross R, notice R point lives in the plane, omega lives perpendicular plane in the Z direction. So this becomes omega times omega dot R minus omega dot omega times R. Okay. All right. Now, All right, so because r lives in the plane and omega lives in the z direction, this part is 0, and this part survives, and this just equals minus omega squared. When we write omega squared, well, remember omega just has one non-zero component, the z component, so we're just squaring it, times r vector b relative to a. So this term is here, and this term, sorry, is up here. So that's where it comes from. The book kind of just says, well, it's a rotation, and then so the velocity should look like a rotational velocity, and the acceleration should have both centripetal and tangential component, which is true and captures the physical essence of it. But here's the kind of, I guess, the math sort of derivation. It also gives a suggestion for what you would do if you had to do a three-dimensional problem, which would be even more fun. Okay, so going back to the book, what they say is that you take the derivative of the absolute velocities and the relative velocity, and there should be a subscript b, I'm just noticing here, sorry. And that will give you the acceleration, and in general you should expect both. So the acceleration at b should be the acceleration of a plus the tangential and centripetal or normal, or I usually call it radial components of acceleration coming from the relative rotations. So just to really highlight it, this part is, this point will be tangent. This is a, b, a, parentheses, t. And this part over here is the centripetal term, so which your book calls the normal term, a, b slash a, normal. All right. So that's the, so this is graphically what they're just trying to indicate. Just like you could break velocities down in terms of relative velocity, or sorry, an absolute velocity and a rotation. Now it's going to be an absolute acceleration plus the types of accelerations you get for rotations, tangent, normal components. Okay, so hopefully that all kind of makes sense and hangs together for you. They're really just saying out in words what I derived. Yeah. Okay. So these problems. So what are you going to have to do for this? In order to figure out, so kind of, well, so you'll notice that if you want the acceleration, it's not enough of b. It's not enough to know the acceleration of a and maybe alpha. You also have to know omega. And that means that for many problems, you're going to have to not only solve for acceleration stuff, but you're also going to have to solve for velocities of components. And you may say, well, that's no big deal, because if I know the velocity of something, I can probably work out its acceleration. The issue is that when you have multiple things linked together, and let's say you want the acceleration of the third point or fourth point, that means you have to track through the velocities. You have to come up with a chain of relative motions. So you have to pick a bunch of points that you can handle. And then for each one, you have to find their separate velocities and accelerations. And you have to push that all the way through the sequence of related points so that you can ultimately come up with the final value of omega for the final point and the final alpha. So the problems just tend to be, they get big very quickly. All right. So that's how that one goes. Right. So because these problems are kind of large and complicated, you want to make use of points which have motions that are tractable. Okay. You don't want to choose and find the motions of random points that go through weird curves. You want to use pinned points because they don't move. You want to use points which go along circular paths or points that go along linear paths, because other points are going to be pretty awful to work out. Your final answer might be one of these other points, like, this point here in the middle. But the thing is, if you use this point in the middle, that's okay as a final answer. But if you want to use that and then find something else relative to it, because the motion of this is going to be quite complicated, the answer you get is going to start, even if the final answer is simple, the algebra in the middle of the problem is going to be pretty gross. So you want to use points which are, so you don't want to use that point. If I was looking at this, I'd be thinking the pinned point, the circular moving point, and the linear moving point. Those would be the points I'd want to track and try to use that, any information I can to figure out what they are doing. And then once I knew what they were doing, I could figure out other quantities. And these problems, when you're making your choices and you have to choose between a cookie and a kick in the head, there aren't many cookies, but there are a ton of kicks in the head. So it's really important to know the difference. Okay, so the general plan is going to be, you got fix a coordinate system, and you want to draw how the objects are moving. You want to indicate the directions of accelerations, omega, angular variables. Be very careful with your minus signs. I'm going to pretty religiously stick to math conventions. And I notice I oftentimes get my angular quantities reversed from what the textbook gets. When I go and compute linear quantities, we all call right positive x and up positive y, and so there's never, the accelerations come out okay. The angular quantities you got to be careful with. And then you also want to write down the relative vectors between things carefully. This is, remember I said I had a mistake in my problem. I had dropped a minus sign in one of the relative vectors going from one page to the next, and it really set me back. All right. And then if things move in curved paths, then you should expect both radial and centripetal and tangential accelerations. And then you're just going to have what I would suggest is look at the data you have, think about what you want, think about how you could kind of go from convenient point to convenient point to convenient point to map out the accelerations in the system and velocities in the system to answer the question that they want you to answer. Okay. All right, so here's our first example. So this is a rod. It's going to, with rollers, the rollers are going to stay attached to the surfaces. So the point A is going to slide down, and they give us a velocity and an acceleration at that moment. And then this is going to roll along the ground. The length of the rod is 5, and the height is 4. So this must be 3 meters because it makes a 3, 4, 5 right triangle. That's kind of convenient. They give me accelerations and velocities. Notice these are both down, so I would say that the velocity of A is negative 6 meters per second y hat, and the acceleration of A is negative 5 meters per second y hat. Okay, so just trying to be really careful with the minus signs. And then let's go through this. Actually, I know they give us least part of the solution. Oh, what are we trying to find? We're trying to find the angular acceleration and the acceleration. So the angular acceleration of the rod and then the acceleration of the point B. Okay. Okay, so take a second and try to solve it. Why don't you pause the video? Then I'll go on a new slide and show you how I did it. Okay, so let me kind of come up with a little bit of a cartoon. I've got a point A, I've got a point B, the rod between them, and this is a 4, and this is a 5. Okay, 3, 4, 5, right triangle. And I've got point A up here, and I've got point B down here. I've got the velocity of point A is negative 6 meters per second y hat, and the acceleration of A is negative 5 meters per second squared y hat. Now, we have lots of information about point A. So we're going to start with point A and leverage that information to figure out what's happening for B. So let's kind of write down our formula for that. The acceleration at point B would be the acceleration at point A plus you would have the tangential component. That's going to be alpha AB cross R B relative to A. And then I have the centripetal term. Okay, so what are the things that we know? Let's kind of underline the things we know in green for good. We know this, and well, we don't quite know this. Maybe I'll put this one in yellow, but it's not hard to figure it out. They basically give it to us. So this is a yellow, and this is a yellow. Those are easy. And then, what are the red line things we need to figure out? Well, we don't know omega, and we don't know alpha. All right, so let's handle the red things, or sorry, the yellow things first. Okay, so let's start with R B relative to A. So that's the relative vector from A to B. Oh, this was a 3, 4, 5. The 5 is on the hypotenuse, sorry. Okay, so the relative vector of B relative to A is going to be down and to the right. So that's going to be 3x hat minus 4y hat. So that one's done. Okay, so I can check that one off the list. And next up, let's kind of rank them. Which one of these things do we have a general method for finding? Well, so far, we've said nothing about finding alphas, but we have figured out things about relative velocities and therefore angular velocities. So to do that, so I'm going to focus on omega first, because that's going to give me well, okay, so that's something I think I can manage. The reason I think I can manage that is because this object rotates in a rigid fashion, and I can use an instantaneous center of motion analysis. So I could, so I know that point A is moving down and point B is moving to the right. If I draw the perpendicular lines of action, I know that the instantaneous center is right here. And so I know, in particular, that the velocity of A equals omega cross r of A relative to the instantaneous center, or since really I just care about the magnitude anyway, because I want to just square it, you could just take magnitudes of everything. And this tells me that that I have 6 meters per second equals omega times r8, the distance here. Well, that's the distance from the center to A, that's just 3. And there you get the omega AB equals 2. And that'd be radians per second. Okay, so now I've handled that. What about this? Now, I don't have any real tricks at this point to solve this without knowing lots of other stuff. So let's just count our unknowns. This is a vector equation in 2D, which means it has 2 components. So even though it looks like it's one equation, one line, it secretly is actually 2 equations for the separate components. On the other hand, we know that B can only move in the x direction. So that's one component, but I have 2 equations here. That means that I can use the leftover equation to solve for alpha, which only has one number really in it. So in fact, even though I don't know alpha and I don't know this acceleration, because they only each have one component, this vector equation is enough to solve it. So the plan is then to write this down and look at the coefficients and solve for the unknowns. Okay, that's the plan. Okay, I think I'm going to give myself a new slide here and go from there. All right, so I know, I'll go and write that down again. The acceleration of A equals the acceleration, of B equals the acceleration of A. And then I'm going to start putting in the things that I have. Well, I'll just write the general expression first. Plus alpha cross R B relative to A minus omega A relative to AB squared times RB relative to A. Okay, and just start writing things down. I know that this is only in the x direction, so I can write that as AB in the x direction equals this part, which was only in the y direction. That would be a -5 meters. You know what? I'm going to not write the units. It's already going to be cluttered enough. And this would be in the y direction. And then I have plus, I don't know what alpha is, so I just assume it's some unknown thing, alpha, but I know it's in the z direction. Cross this vector, which was 3x hat minus 4y hat minus, I found the angular velocity to be 2. 2 squared is going to be 4 times 3x hat minus 4y hat. Now, I find it useful, rather than using the determinant method, to just remember that x hat cross y hat equals z hat. Y hat cross z hat equals x hat. Z hat cross x hat equals y hat, which means these are the positive ones, and the other ones are negative. So I'd have y hat cross x hat equals minus z hat, and I would have z hat cross y hat equals minus x hat, and x hat cross z hat equals minus y hat. So I find it useful just to kind of know those things, because I'm going to have to multiply through with these vectors and take the cross product. I'm going to get z times x. Z times x, oh, there it is, it's plus y. So this first one's going to give me a plus y. And then I have z times y. Z times y is a negative x, but there's already a minus sign there, so I'm going to get a double negative and it'll come out positive. So this is going to tell me that AB x hat equals minus 5 y hat plus, and I'm going to get 3 alpha times y hat, and I'm going to get plus 4 alpha, because of the double negative, x hat, and then I have minus 12 x hat minus plus 16 y hat. Okay, now I just regroup and find coefficients. So I write x hat, and what has an x hat in it? Oh, there's a 4 alpha and a minus 12. And then I have a y hat multiplying. There's a negative 5 plus 3 alpha plus 16. All right, and I notice that there's no y component over here. So that tells me that the y component must be 0, and that tells me that alpha equals 11/3. Negative 11/3. Hold on, let me check my minus signs. Yes, that makes sense. It'll be a negative 11/3. Why did I say this makes sense? Well, if you think about it, what's going to happen is it's going to swing down, right? We all know that. So we know omega will be positive. However, when it's done, when it lands, so it kind of rotates. How do I say this? It starts. Imagine it started from rest. It would start out gaining speed very quickly. Then as it goes farther and farther down, it actually would not rotate as fast. It kind of, the acceleration slows down towards the end. Sorry, not the angular velocity kind of slows down towards the end. It becomes more linear, less rotational. And if omega is decreasing as it falls, that means alpha will be negative. So that's a reasonable conclusion. Okay, so now that I know alpha, I can back substitute into here, multiply it out, and then get the acceleration of point B is, now when I do this, I get 4 times alpha equals negative 12. So that's going to be 12 clear, 4 alpha. So that's going to be minus 44 so that becomes, plugging that in, that becomes, when I plug it all in, I get, I actually get negative 26 26.7 meters per second squared. I'm going to plug it all in. Let's see what they have. So they've gone through, and it's basically the same steps. They may have done the algebra a little differently, but it really is the same. And it's like a miracle. See, so 26.7 negative, and the rotational thing is that way. Yeah. So very good. So just to compare. Oh, so if you type in negative 11 thirds, that's just negative 3.67 radians per second squared. So that's the same answer that they had. Okay. All right. Some observation points or things that you can observe when you have two surfaces that are both rotating and or I guess you should just say they're both moving along different paths, let's say, but they're in contact. They have a contact point which doesn't slip. That contact point, without slipping, forces their tangential velocities to be the same at that point. It also forces their accelerations, their tangential accelerations, to be the same at that point. So, but that doesn't mean that the normal accelerations are the same at both points. That was the question from the quiz that was what they were getting at. When 2 points are in contact, their tangential accelerations must be the same, but not their normal accelerations. One, which I'm surprised they didn't really spell this out. One important consequence of that is the case where you have two circles, but what if you made this gear bigger and bigger and bigger and bigger? Eventually, the larger gear would look flat, and the smaller gear would look like a ball. And what that tells you is that at the point of contact, well, the accelerations, the tangential accelerations must be the same. So call this ATAN1 and call this object 2. But, okay, so now if you take object 2 to be something so gigantic, take it to be something like, I don't know, the Earth, so big, that tells you that the tangential acceleration at the point of contact must be 0. That's really useful to know whenever you have something, because we'll have lots of problems where it's like a ball rolling on the ground or a wheel on the ground. And it's useful to know that the tangential acceleration of the contact point with a moving object rolling on an object that isn't moving must have 0 tangential acceleration. Now, if you accounted for the motion of the Earth, and then you had the motion of the ball on top of the Earth, then all of a sudden you would get an acceleration maybe at that contact point. Because the only thing you're really guaranteed to know is that the two have the same accelerations. But if you can ignore the motion of, say, the Earth, then the ball must also have 0 tangential acceleration at the contact point. That doesn't mean that the tangential acceleration is 0 everywhere. It's just at that contact point. What it does have is normal or centripetal acceleration. If you were to follow a point, let me see, I'm not sure if the book has, did it give us a picture of what happens when something rotates? They don't really do that. So I'll draw a picture. I apologize for my artwork. When you have an object that's rotating like this, and you follow a point as it rotates, what you actually see, and you kind of trace out the trajectory of this point, is it does something like this. and um, and you've also kind of, well, all right, just leave it like that. So look what's happening when the point when the wheel rotates and this point comes in contact with the ground, it actually approaches the ground going straight up and straight down. And then it pops back up, and then it moves forward, and it goes straight down, and then it pops back up, and then kind of has that sort of pattern. That means that whenever this point is touching the ground, there's no um, sideways acceleration. All the accelerations are up and down. So that tells you that the tangential acceleration is zero whenever for this point, whenever it is touching the ground. There is acceleration when it's up and moving around the top of the circle, but not when it's touching the ground. So that's just a useful thing to know. I don't know. I think they didn't quite spell it out in this slide, but that's just handy to know. Okay, here we have objects rolling without slipping. Um, um, it's just going to have you do this. It's a nice point. You know, when you have something that rolls without slipping, what you can do is say that point A here at the bottom is the instantaneous center of motion. Use that to find the angular velocity of point G, and then you also know that at point A, the acceleration in that instant is only centripetal acceleration. There's no tangential acceleration. That's what I was just talking about. And so those are some extra facts you can use to simplify your work. Oh, sorry. So they're just going through and working that out. They're saying A is the center of instantaneous center of motion. And so it has zero velocity. So then you can write the velocity of G like that. Because you know the center of this ball or this wheel can only move horizontally, it allows you to just relate the scalars rather than carrying around the vector information the whole time. Once you find omega, then you're going to plug it into here, and then it's very much similar to what I did. Here we go. They're saying in words what I was trying to show you. So they say, since G moves along a straight line path, just before A touches the ground, its velocity is directed downwards, or just after contact is directed upwards. So they're saying that at the point of contact, there's no forward motion. It only has vertical motion. In fact, remember that, if you kind of remember that sort of pattern I have, you can kind of see they've kind of traced in the paths there. So that's what those little blue lines are trying to show you. I wish they'd kind of draw your attention to it a little bit better. And then because the acceleration is only in the y direction, again, that allows you to have one fewer component of the acceleration around, and then that vector equation becomes enough to solve for whatever unknowns you have in the problem. You really have to be careful and count your knowns and unknowns in some of these. All right, here's the following example. We have a gear wheel, or a wheel with gear teeth rolling on a rigid or fixed surface. We're going to assume that the rack is not moving. The center we're going to call O. They give us the radius. They give us the angular quantities. Notice, I'm going to correct their conventions here. I'm going to say, because both of these are clockwise, I'm going to say that alpha is actually -6 radians per second squared. I'm going to say that omega is -12 radians per second squared. That way I've anchored my conventions to the math convention, and that should help me get started. the goal in this problem is to find the acceleration of the point at the top of the wheel, and yeah, that's it. Okay. Now, they did this in 2 steps, well, or in a different way than what I did. They used the fact that this is the instantaneous center of motion to figure out the motion and acceleration of point O, and then use the relative acceleration to figure out what happens at A. I think that's a kind of overkill, or just a little long way about. So I'm going to do it, I guess, a slightly different way. Oh, sorry. And so what I'm going to have, so I'm going to draw in, I've got a wheel, and I've got numbers here. I'll write those down. Look at those. And I'm going to say the instantaneous center of motion is here. Up on top, I have point A. That's what we want to know about. I'm going to say, oh dear, where are my numbers? There we go. I'm going to say that, so I have a radius, which was 0.3. I have alpha, and that was meters. I have alpha, which was -6 radians per second squared. And I have omega, which was -12 radians per second. Very good. Because I know that this point has no horizontal acceleration, that's fine. Let's see. So the that can kind of help me. Furthermore, I know that it only has centripetal acceleration. So I know that the acceleration at the contact point with the ground is just going to be omega squared r and times y hat, and it has to point towards the center of the circle. So that's the absolute acceleration at this point. And then I'm going to go through and I'm going to say that the acceleration of A equals the acceleration of the instantaneous center, and I'm going to say plus alpha cross r c minus omega squared. Now, what are the things that I know? I know this. Put those in green, I guess. That's what I was doing before. I know this. Well, this distance is just twice the radius, so I know that, and I know that, and I know omega. The problem gives that to me, and I know alpha. So this actually is a pretty easy problem because almost everything is just given to me. So I can work this out, and I can simply say, let's see here. So this becomes omega squared r in the y hat direction plus, so think about it, this is in the y direction, this is in the z direction. When I take the cross product, I'm going to get something in the negative x direction. So I'm going to get alpha times this distance. This goes all the way from the center up to here. That's going to be twice the radius times negative x hat. And then this is going to be minus omega squared. And I get, this is twice the radius times y hat. So I can pull this all together and get minus omega squared r, using lowercase r, y hat. I get a plus 1 here and a minus 2 there, so I get a negative 1 times omega squared r, y hat, and I get minus 2 alpha r, x hat. Does that make sense? Well, let's think about it. Omega and alpha both go that way. So look at what happens. If omega were to spin clockwise and alpha were to grow in the clockwise direction, so they became more and more negative, that would actually propel the wheel forward faster. So for me, I suppose this one's a little tricky to understand. But it has a square, so it's always negative. It's negative definite. But anyways, for alpha, at least it makes sense intuitively. Because if I make alpha bigger and negative, this term becomes more positive, and the wheel will go faster. All right. So I can just plug in numbers here. I've got all the numbers. And this becomes negative 43.2, it'll be meters per second squared y hat, plus 3.6 meters per second squared x hat. So it has both components. You might say, well, wait a minute. This wheel is moving sideways. Why does the acceleration have both a vertical and horizontal component? And that's because we're not talking about the point at the center of the wheel. That point only can move sideways. The points on the anywhere else in the object go up and down, up and down, up and down. So at this point, the object has both a radial or centripetal acceleration, which points down to the center, and it has a radial component, a tangential component, which propels it forward. This is the tangential component of acceleration, which is what propels the wheel forward. Let's compare this to how they did it. If I remember right, they went through a different analysis. They used the instantaneous, let's see. So they went through and let's see how. They don't really give you a simple explanation of that. They're just going back to this analysis and they're analyzing the motion of the center relative to the edge. And you really have to go through and do this algebra to really derive the result. So maybe this is, I guess I use this result. This is also true from the other component equation. So the point on the contact point moves with only centripetal acceleration. The center here, well, it looks like it's rotating about the center of velocity, so therefore you only get, well, that's even hard to say. Yeah, you just have to do the algebra. I think that's about the best I can do on that one. All right, so they're using that formula here to find the acceleration of the center of the wheel. That's my work. And then based upon the motion of the center of the wheel, they're using the relative motion formula to figure out the other point, the point at the top of the wheel. So they have the center of the wheel here. Alpha is the same, but they have a different radius. Their radial vector goes from O to A, whereas mine went from the contact point up to A. And then omega is the same as what I used, but then again, they have a different vector. But in the end, we get the same answer. The same answer. So I guess it's just reassuring you can do the analysis in different ways, and you get to the same spot. All right, here is your reading quiz. So I'm going to start our discussion with this. Ball rolls without slipping. Select the tangential and normal components of the relative acceleration at point A with respect to G. A with respect to G. Think about how you would do that. You'd want to find the acceleration of A, and if you could find the acceleration of G, then A relative to G would be that'd be the acceleration of A minus acceleration of G. So see if you could find that. All right. And super brownie points if you go ahead and start thinking about the problem that's going to come up next, the group problem, because it's going to take us a while to work through it as a group. So if you could go ahead and start it, I think that will really help. So here's your problem. All right, so I will stop the video now, and I will talk to you guys on Tuesday. All right.